We have finished our FRQ topic review, and today we're starting our multiple choice topic reviews. Topic 1 is on limits, continuity, and differentiability. So I have a notes page for this. For some of these topics, for most of these topics, we will just do some problems from the worksheet for notes. I won't have a separate notes sheet, but for this one, I thought it was good to review some of these concepts that we have not seen since August. So let's take a look at some of these. First of all, we say that a limit is equal, the limit of f as x approaches a is equal to some number if and only if the limit from the left is equal to the limit from the right, and that's equal to that same number. F has a horizontal asymptote of y is equal to a, that would be the equation of the asymptote, if the limit as x goes to infinity or negative infinity of the function is equal to a. And that makes sense. If as x goes to infinity, if we're approaching a number, that means we have an asymptote, a horizontal asymptote. F is continuous at x equals a if and only if the limit from the left is equal to the limit from the right, and that is equal to the function at a. All three have to be equal for f to be continuous. There's a special term for a discontinuity that has a hole, and that is called a jump discontinuity. And that means that the limit from the left is equal to the limit from the right, but not equal to the function value. That would mean you have a hole. Okay? We have three reasons that f might not be differentiable at some value of x. So these are the three reasons. If f has a vertical tangent at x equals a. If f has a discontinuity at x equals a, that might be a hole, a vertical asymptote, or some other kind of break in the graph. We're not differentiable there. Or if the slope of the line tangent to f from the left of x equals a is not equal to the slope of the line tangent to f from the right of x equals a. So that would mean that the limit from as x approaches a from the left of the derivative is not equal to the limit as x approaches a from the right of the derivative. If that happens, we say that f has a cusp at x equals a. So let's take a look at some examples of multiple choice questions that you might see. In this first one, we were just asked to find the limit as x approaches 2. It's a piecewise function, so we are going to need to consider from the left and from the right. And I notice that 2 is where these two these two pieces separate. So from the left, we are using this section, so I'm putting 2 in place of x here. So that would be natural log of 16 divided by 2. Okay? From the right, we put 2 in here. This will be 2 ln of 2. So the question is, are those the same? Are they the same? Well, we're going to need to apply some log properties to see if they're the same. I know that I can move this coefficient to be the exponent on the argument. So that would be ln of 2 squared, or 4. This is the same thing as 1/2 natural log of 16. And again, I can move this coefficient to the exponent, make that 16 to the 1/2 power, which is the square root of 16, or 4. So clearly those are the same. Our answer choice there would be A. So that's something that AP might do. In the second problem, the graph of the function g is shown. For what values of x is g not differentiable? Not differentiable. So here's g. The first interesting point is right here. G is not differentiable there because we have a cusp. So at x equals -4, we have a cusp. That doesn't narrow it down because everything has a -4 in it. The next interesting point is right here, where we see another cusp. The slope from the left is not equal to the slope from the right. So at x is equal to -3, we have another cusp. So I can get rid of this one because that doesn't have a -3 in it. Okay, right here, when x is -1. When x is -1, the slope is 0. That's not a reason for it not to be differentiable. In fact, that's a nice differentiable point. We have a slope of 0. So at -1, we are differentiable. So this one is not going to be our answer. Right here, at x equals 1, I see a vertical tangent line. There's a vertical tangent line there. So we are not differentiable at +1. And that's going to be my answer. Number 3, which of the following limits are equal to 0? Well, in each of these I see x is going to infinity. So those we got super good at when we were doing series because n was always going to infinity in all of our series tests. So as n goes to infinity, as x goes to infinity, that won't matter and that won't matter. The only terms that matter, the only significant terms are those terms. The x's totally cancel out and we're left with 5/3, not 0. Okay, on to this one. Well, the 4x and the 10 are insignificant. The 3x is insignificant. I'm left with this. The x's reduce. They don't cancel out completely. They reduce, and we have 5/3x. And as x goes to infinity, that is going to 0. So we have 2 as an answer. Over here, let's see, the 4x and the 3 don't matter. The 15 doesn't matter. As x goes to infinity, so this reduces to 5x/3, and as x goes to infinity, that goes to infinity, not 0. So the only one that goes to 0 is 2, D. Okay, cruising along. This is so different from the FRQs because each little problem is short, sweet, and you're done with it. Which of the following equations has a horizontal asymptote of y equals 3? Well, if they're asking me about horizontal asymptotes, I know I need to take the limit as x goes to infinity or negative infinity. So for each of these, I'm going to come in and let x go to positive or negative infinity. It's easy to do. We got really good at this. Doesn't matter, doesn't matter. This reduces to -3, not 3. So not number 1 here. The limit as x goes to positive or negative infinity here, doesn't matter, doesn't matter. This reduces to 3x/1, and as x goes to infinity, that would be either positive or negative infinity, not 3. And for this last one, doesn't matter, doesn't matter. Reduces, the x's reduce out completely, and we reduce to 3. So the only one that goes to 3 is the third one, so that's our answer, choice B. Okay, number 5. For what values of k is h continuous? Well, each of these by themselves is continuous. So the only place that they might not be continuous is when x is 3. So if we want to find the value of k that makes these continuous, we need to put 3 in for x and solve for k when we set these equal to each other. So I would have 9 times k plus 3 is equal to 12 plus 4. So we'd have 9k is equal to, this is 16 minus 3 is 13, so k would be 13/9. C. A little limit. X is going to 4, so I begin by putting 4 in for x. On top, we're going to 0. When we put 4 in here, 4 cubed is 64, so the bottom is also going to 0. Back in Unit 1, we did not know L'Hopital's rule, but this is a perfect L'Hopital's rule. So I'm going to apply L'Hopital's. Keep your limit. Take the derivative of the top. It's just 1. The derivative of the bottom is 3x squared. Now we put 4 in again, and we get 3 times 16 in the denominator. That's 1 over 48. When we did this problem back in Unit 1, we had to factor that denominator. It was a difference of cubes, so we needed to know how to factor a difference of cubes there. Okay? Number 7, which of the following is equivalent to pi over 2? All right, we're going to infinity or negative infinity with this arctan. We know these values because we're familiar with it for arctan, right? The graph of arctan has these horizontal asymptotes at positive pi over 2 and negative pi over 2, and it goes like that. That's the graph of arctan, y equals arctan. So as x goes to positive infinity, we're going to pi over 2. As x goes to negative infinity, we're going to negative pi over 2. For cosine, for our cosine, we want to know what's happening as what is arc cosine of 0, essentially. So arc cosine of 0, I think what angle makes cosine 0? Well, and we have to be between, we have to be in quadrants 1 and 2, or on an axis. So cosine is 0 at pi over 2, and that is right here. So this is going to be pi over 2. That's my thought process on that. You might think of it a little differently, but the answers here would be 2 and 3, C. All right, the graph of this function has, and then we have an infinite. Infinite discontinuity would be a vertical asymptote. Removable discontinuity would be a hole. A horizontal asymptote, we know what that is. And a vertical asymptote would be the same as this infinite discontinuity, so I'm not thinking that's going to be my correct answer. Let's begin by doing something that we can do. I'm going to factor the numerator, factor the bottom. I want to see if I have a hole. That's my thought process. See if we have anything going on here. So, or we might see an asymptote of some sort. So I'm going to factor an x out of the numerator. And on the bottom I have a difference of squares. I can further factor that numerator into x plus 3, x minus 2. And sure enough, I see I have a hole at x minus 2. That's a removable discontinuity, so that's B. So just know that a hole is a removable discontinuity. All right, which of the following statements is true? The limit as x approaches negative 2 exists. That would mean that the limit from the left is equal to the limit from the right. But in this case, all we need to do is apply this because we're not interested in x equals negative 2. We're only interested in x approaching negative 2. So we would plug negative 2 in here. So what happens when we plug negative 2 in there? Well, if I plug negative 2 in here, I'm going to have 3 times 4 is 12 minus 12, which is 0 on top, and I'll have 0 on the bottom. So I don't know if that exists. I'm going to need to use L'Hopital's because I got limit on the top is going to 0, the bottom is going to 0. So the limit as this will be the limit as x approaches negative 2 of I'm applying L'Hopital's. So the derivative of the numerator is 6x. The derivative of the denominator is 1. Now put negative 2 in, and yes, it does exist, and we have negative 12 for our answer. H of negative 2 is just right here. I just need to put negative 2 in for x. I know that that's going to exist. And then here in 3, h is continuous at x equals negative 2. Well, h is continuous if this limit is equal to h of negative 2. So I am going to need to go and plug that in after all. 4 plus 4 minus 20, that's 8 minus 20 is negative 12. Those are the same, so yes, H is continuous. All three are true. Okay, just a few more here. Goodness, these are stuck together. Okay. Number 10. All right, if f is a continuous function on the closed interval between a and b, and f of a is less than f of b, which of the following must be true? This sounds a lot like, when this setup sounds a lot like the intermediate value theorem. That's my first thought. Because we're continuous, which is the only criteria for the intermediate value theorem. It's the only condition. And they're talking about y values, and we know x is between a and b. It sounds exactly like IVT, so that's what I'm expecting. So IVT essentially says, if this is the point when x is a, if that's x is a, then the y coordinate would be f of a. That would be that point. And over here we have when x is b, but they tell me that the y coordinate is bigger than this, so we would be up higher, right? So this would be the point b, f of b. And I don't know what the function looks like at all, but I know that f is continuous between here. So if it's continuous, I don't know what's going on, but I know it's continuous. Okay? So I know that for some c value in between, for some c value, f of c has to be between f of a and f of b. F of c is between f of a and f of b, and that's sitting right here. So that answer would be B. Intermediate value theorem. We also covered that in there. If the function f is continuous at x equals a, which of the following must be true? The value of f is less than the limit? No, absolutely not. It has to be equal to the limit. The limit from the left is not equal to the limit from the right? Nope, it has to be equal. The derivative of f at x equals 3 exists. If f is continuous, do we have to have a derivative there? No. We could have a cusp or a vertical asymptote. The derivative would not exist, but we would be continuous. This last statement is the definition of continuity. So that's definitely our answer. One more here. Let f be the function defined by this function. Which of the following statements is true? And I see we're talking about continuity and differentiability. So it would be sure nice if we knew what this graph looked like. Are we familiar with this graph? I'm familiar with, if the absolute value was not there, I'm familiar with the graph of the square root function. At x equals 2, we would be at 0. If you're not familiar with it, plot some points. When x is 2, we're at 0. When x is 3, we're at the square root of 1, which is 1. If we go 4 units away, we would go up 2 units. So that would be that side. Now what if x was negative 1? Well, if x was negative 1, if x was positive 1, what if x was 1? We would have a negative 1 in here, but we have the absolute value, which would be back to positive 1, square root of 1. So we're going to be looking like that. So are we continuous? Yes, we're continuous. Are we differentiable right here? No, we're not differentiable. We're continuous, but not differentiable. That's our answer choice A. So it would be totally impossible for me to give you an example of all different kinds of multiple choice questions. I just wanted to share with you a few so that you can go and do your assignment and get a little bit of a feel for multiple choice questions on this topic.